Okay. So, hi everyone. So, good morning all. Right. So, first of all, let me know whether audio and video everything clear. See, if it is not clear, please let me know in chat box here. Please let me know in chat box. Okay. So, give some comments in chat box if it is not clear. So, I hope audio and video everything is clear. I hope so. Right. Okay. Okay. So, in the previous session I have explained about time harmonic waveforms, yes or no? Okay. So, in real time how they are going to look like, and in complex form how they are going to look like. So, all those things I have explained, yes or no? Okay. So, time harmonic waveforms, how they are going to look like here in real time. Time harmonic means what? Time harmonic means the fields are varying sinusoidally with respect to time. So, those type of fields we call it as what? Time harmonic fields. So, in real time we can represent it as what? In terms of what? In terms of sine and cos. So, that is A into cos of what? A into cos of omega t minus beta x, or I can represent it as A into sine of what? A into sine of omega t minus beta x. And in complex form, we can represent it as what? We can represent it as A into e power j of omega t minus beta x, right? Okay. So, here I have represented A with what? A with A dash, where A dash is nothing but what here? A dash is nothing but A into what? A into e power j phi. Understood? So, that means this amplitude is what? In general, this amplitude is complex in nature. In general, this amplitude is in complex in nature. Understood? Okay. So, these things we have seen here, how to represent the time harmonic fields in real time, and how to represent it in complex form. Okay. So, these things we have seen. So, here we have also seen that this beta, what we got here? Beta is equal to 2 pi by lambda. We call this beta as what? We call this beta as a phase constant, and its units are nothing but what? Radian per meter. So, how we got this value 2 pi by lambda? All those things I have explained in the previous session itself. Understood? Okay. Okay. Okay, phase constant. So, that is a 2 pi by lambda. So, how we got this 2 pi by lambda value? All those things I have explained in the previous session itself, right? Okay. So, next another one we have seen that velocity of the wave, we got it as what? Ratio of what? Ratio of omega by beta. Understood? Okay. So, this also we have seen here, how we are getting this expression and how we are getting this value. So, all these things we have seen in the previous session itself. Understood? So, you have to revise all these things here. So, and also I have explained that how the wave equation will looks like. How it is going to look like here? Dou square f of x comma t by dou x square is equal to what? Is equal to 1 by v square into dou square f of x comma t by dou t square. So, in this manner the wave equation will looks like. Here v represents the velocity of what? The velocity of the wave. So, what is the solution of this wave equation here? The solution of this wave equation is nothing but what? A wave function. So, any function which is of this form, f of beta into plus or minus vt plus or minus x will become what? Will become the solution of this wave equation. Yes or no? Okay. So, any function which is of this form will satisfy what? Will satisfy this wave equation. Understood? Okay. Okay. So, all these things I have explained in the previous sessions here. Okay, lecture number 50 and lecture number 51. So, these two lectures will deal with these things, right? Okay, okay. And in the previous session here, Tirumalai, your lectures is enough for IAS exam. Not only IAS here, whatever may be the exam. Okay, so whatever the topics I am covering, those topics I am covering in detail. Okay, so that is more than enough. Right? Okay. So, f of beta into plus or minus vt plus or minus x, right? Okay. Okay. And I have started transmission lines. In the previous session, I have started transmission lines, okay. So I will represent in this manner here, transmission lines I will represent in this manner, okay. So this is my notation here, this is my notation, okay. So transmission lines, right, okay here. So now here we have seen that different types of transmission lines, that is two conductors, we have considered two conductors separated by what? Separated by some dielectric medium, right, okay. So this is a power transmission line, we have considered this as what? Power transmission line, which is operated at what? Which is operated at low frequencies, that is at around 50 Hz or 50 Hz to what? 50 Hz to 60 Hz, 50 Hz or 60 Hz, okay. So under this frequency range it is used here at low frequencies, okay, power transmission line. So next we are having another type of transmission line, that is nothing but what? That is nothing but coaxial cable, right, okay. So here this region is conductor and outside region is also conductor. In between these two, what you are going to have? You are going to have dielectric region, So this is coaxial cable, which is operated in the range of what? In the range of megahertz to what? Megahertz to gigahertz, okay. So next I have said another type of transmission line, so that is nothing but what? That is nothing but microstrip transmission line, which is operated at what? Which is operated at very high frequencies, understood, okay. So this region here, the shaded region is nothing but conducting region, okay. So this shaded region is nothing but conducting region. So this region between this conductor and between this conductor, the region that is present is nothing but what? Is nothing but dielectric, So this is operated in the range of what? In the range of gigahertz, So this is microstrip, transmission line, and this is coaxial cable, and this one is power transmission line. So these are the different types of transmission lines we are having, understood, okay. So what I have told here, we are not going to study particularly about any type of transmission line. We are going to study the transmission lines in general here, understood. So that means if you observe all the transmission lines here, what we can observe here? What is the common characteristic of all the transmission line we can observe? See here, if you observe power transmission line, here you are having a conductor, here you are having a conductor, separated by what? Separated by some dielectric medium. Similarly, if you consider coaxial cable, here you are having a conducting region, and outside also you are going to have a conducting region. In between these two, you are going to have what? Dielectric region. And here if you observe microstrip line, here you are having a conducting region, here you are having a conducting region. Between these two, what you are having here? A dielectric region, okay. So what is the common characteristic of all these transmission lines? Is nothing but two conductors. You are having two conductors separated by what? Separated by some dielectric medium, So we are going to study the transmission lines in general here. We are not going to study about particular type of transmission line, okay. We are going to deal with the characteristics of the transmission lines in general. So that means we are going to consider our transmission line as what? As two conductors separated by what? Separated by some dielectric medium, understood, because this is the common characteristic of all different types of what? Of all different types of transmission line, understood, okay. Yeah, so that's what you have to understand. So this is transmission line we are going to consider. So this transmission line is going to act like what? This transmission line is going to act like a guiding structure. Okay, so it is going to transport the signal from where to where? From source to, on one end you are going to connect source, and on other end you are going to connect what? You are going to connect some load. Okay, so the signal will be transmitted from source to what? From source to load through this guiding structure, that is nothing but transmission line. Right, okay. Funny, good morning, Funny. Okay. Yeah. So now I have told that all these things here, all these things I have explained in the previous session itself. Just I am revising all those things. That's it. Okay. So in this session here, in this session, we'll mainly study about what? We'll mainly study about transit time effects here. Transit time effects. Okay. Transit time effects. So this is what we are going to study in this session, right? Okay. And if possible, I will start distributive nature along the transmission line also, if possible. Okay. But first we will complete this transit time effects. See here, yesterday I have asked one question, that is whenever you are dealing with circuit theory, whenever we are dealing with circuit theory, or you can say network theory, whatever it may be. Okay. So if you consider a signal, voltage signal here, and here let us say this is load, that is resistance, or let us assume here we are going a time varying voltage signal is applied, and here the current flowing is I of t, and let us say the length of the circuit is L, the length of the circuit is L. So here whenever you are dealing with circuit theory, understood? So what you will see here, what you will observe, so always you are going to deal with voltages and currents that are varying only with respect to what? That are varying only with respect to time. You are going to neglect what? You are going to neglect the length of what? The length of the circuit whenever you are dealing with the circuit theory. Understood? So when coming to transmission lines here, when coming to transmission lines, you are going to have here source, right? Okay, source, and here you are going to have some load. So let us say the length of the transmission line is L. Okay. So in this case, whenever you are dealing with the transmission lines, always you will consider the currents as a function of what? The currents as a function of length as well as what? Time. That means current is a function of both space as well as what? Time. And the voltage is also, you are going to consider it as what? Function of what? Function of both space as well as what? As well as time. Okay. So in circuit theory, you are considering voltages and currents as a function of only time, but whereas in transmission lines, we are considering the voltages and currents as a function of both time as well as space. Why? Understood? Okay, so this is the first question. So next here, whenever they become functions of time, whenever they are functions of only time, you can happily apply what? You can happily apply KVL and KCL. You can happily apply KVL and KCL. So what KVL says here? What KVL says? At any instant of time, the voltage at this source, for this loop I am saying here, okay. So the voltage at any instant of time, the voltage at source will be equal to what? Will be equal to the voltage at what? The voltage at load. Yes or no? This is load now. Yes or no? So the voltage across resistance R will be same as what? The voltage across the voltage at what? The voltage at the source. Yes or no? At any instant of time, the voltage at the source will be same as what? The voltage at what? The voltage at load, or the voltage at R. Yes or no? Okay. That is what is called as what here? KVL. That is what is called as KVL. Understood? Okay. So at any instant of time, the voltage available at the source is equivalent to the voltage available at the load. Understood? Okay. So here the KVL and KCL, everything is valid, and they can be happily applied while dealing with what? While dealing with circuit theory. But whenever you are dealing with the transmission lines, here KVL and KCL are ruled out. So you should not apply KVL and KCL. Okay. Whenever voltages and currents becomes functions of length, then you should not apply what? Then you should not apply KVL and KCL. So they will be ruled out. Okay. So why all these differences are happening between circuit theory and transmission lines? Okay. So why means this is because of what? This is because of transit time. This is because of what here? Transit time effects. Okay, while dealing with circuit theory, you are going to neglect what? We are going to neglect this transit time effects. We are going to neglect. But here, whenever we are dealing with transmission lines, you cannot neglect this transit time effects. They will become what? They will become significant here. Okay, so you should not neglect them. So that's why here KCL, KVL, everything will be ruled out, and voltages and currents will become a functions of what? Not only time, they will also become a functions of length also. Okay. Okay. So the main reason is The main reason between these differences is because of what? Transit time effects. Okay, so now we will see what do you mean by that transit time effects, right? Okay, okay. So next, we will deal with transit time. Transit time. First we will see what do you mean by transit time. So transit time I am representing with T suffix R, right? Okay. Okay. See, the definition of transit time is very simple. See here, if you are having, let us say this is source, right? This is source, and here you are having load. This is source and this is load. Let us say the length of this transmission line is L. Let us say the length of the transmission line is L. Okay, so I am considering on this axis, let us assume I am considering on this axis I am considering as x axis. Okay, so let us say this location is x is equal to 0 and this location is x is equal to L, right? Okay, yeah. Okay, so now let us assume whenever you apply a signal, the signal is going to travel from where to where? From source to what? From source to load. Let us assume it is traveling with a velocity v. Understood? Okay, so the distance it has to travel is nothing but what? Is nothing but L. So what is the time it is going to take for the signal to travel from source to load here? What is the time it is going to take for the signal to travel from source to load? See, this distance is nothing but L and the velocity with which it is traveling is v. So therefore the time it is going to take, to travel from source to load, the time taken by the signal to travel from source to load is equivalent to what? Is equivalent to L by what? L by V. Understood? Okay, so this time taken by the signal to travel from source to load, we call it as what? We call it as transit time. So what do you mean by transit time here? So the time taken by the signal, to travel or to propagate, okay, whatever you want you can use here. Okay, so the time taken by the signal to travel from source to load, okay, so is called as what? Is called as transit time. Understood? Okay, okay. Now now let us consider. So this is a definition here. Definition is very simple, you can easily understand. Okay, now see here. Now I am applying some signal at the source. So let us assume the time period of the signal here. Time period of the signal at source is nothing but let us say t. Understood? Okay, and the time taken for the signal to travel from source to load is nothing but what? Is nothing but tr. Understood? Okay, now let us assume I am applying a very low frequency signal here. I am applying very low frequency signal at what? At source. Okay, at source I am applying a very low frequency signal. So whenever I am applying a very low frequency signal means the time period will be what? The time period will be very, very large. Yes or no? Low frequency signal means time period is what? Time period is very, very large. Let us assume time period is very, very large. Okay, so time period is very, very large means what here? The signal is varying very, 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 very slowly with respect to time. So this means signal is varying very, very slowly with respect to time. Signal is varying very, very slowly with respect to time. Okay. Now TR is equivalent to what here? L by V. So L represents the length of the circuit and V represents the velocity of the signal. Let us assume the velocity of the signal is 3 into 10 to the power of 8 meters per second. Let us assume here, let us assume, okay, or you can assume 2 into 10 power 8 meters per second, whatever you want you can assume. Let us assume, okay, let us assume the signal is traveling with this speed, that is 2 into 10 power 8 meters per second. Understood? So and consider that this t is very large, and this t v velocity is very large. Here the velocity is very large when compared to what? When compared to L. Let us assume here v is far greater than what? Far greater than what? Length of the transmission line. Okay, so let us assume length of the transmission line as 100 meters or 1000 meters. Still when compared to velocity, L is what? L is very small. Yes or no? Okay, so that means here TR is what here? TR is very small, very small. Okay, very small. Understood? Okay, so that means the time taken for the signal to travel from source to load is very fast. TR is very small means what here? Within very less time, the signal will be traveled from source to what? Source to load. So TR is very small means the speed of the signal, or the signal is going to travel from source to load with very fast manner. Yes or no? Okay. So TR is very small means the signal travels from source to load very fastly. So this is what you have to understand, very fastly. Understood? Okay. Okay. So now so a very low frequency signal I am applying at the source. So hence T is very large. So this implies signal is varying very slowly with respect to time. And here TR, that is the transit time, the time taken for the signal to travel from source to load, that is L by V. I am considering V is far greater than what? Far greater than L in general here, in general. Okay. So and hence TR is very small. This implies what here? This implies signal travels from source to load very fastly. So now if you compare this time period of the signal and TR here, if you compare this time period of the signal and TR, what you can say here? What you can say? You can say that time period of the signal is very greater than what? Very greater than TR. Time period of the signal is very large when compared to what? When compared to TR. Understood? At low frequency. Understood? If I apply a low frequency signal, then this is the case here. This is the case. The time period of the signal is very much greater than what? Than transit time. Okay. So what happens whenever T is far greater than TR? What happens when T is far greater than TR? Okay, so that's what we are going to see now. Now see here, let us assume here this is the source point, okay, and here this is the load point, let us assume. Okay, so here you are applying the signal which is varying very slowly, understood? Okay. So the time period is very large, the time period of the signal is very large. Let us assume at T is equal to 0, okay. So let us assume at T is equal to 0 here. This is at T equal to 0. At T equal to 0, the source is at this location here. The source is at this point. Understood? Okay. So next what will happen? So at T equal to 0, the source is present at this location. So this signal, this point is going to transport from source to what? Source to load. So this value of the signal is going to transport from source to load. So what will happen here? So at T equal to 0, the point is present here. So this value of the source, this value of the source is going to travel from where to where? From source to what? From source to load. Let us assume it has traveled from source to what? From source to load. Okay, so what is the time it is going to take here to travel from source to load? So it will take TR seconds. So that means at T is equal to what? At T is equal to TR. After TR seconds, this point is going to reach to this location, So within this duration TR here, what is the variation of the signal at the source? See, the signal is varying very slowly. Understood? And the time period of the signal is very greater than what? Very greater than transit time. So that means within this TR time seconds here, the signal may move from here to what? Here to here. So that means almost it is having what? Almost it is having the same value. Let us assume the time from here to here is TR seconds. So that means within TR seconds here, the signal has changed from this value to what? This value to this value. So this is at T is equal to what? T is equal to TR. This is at T is equal to TR. Understood? So after TR seconds here, if you observe the value of the signal at the source and the value of the signal at the load, both are at what? Both are almost at what? Almost at the same value. Yes or no here? Yes or no? See, there is no difference between this value and this value. This is almost same. If it is 10 volts, so this is also at what? 10 volts. So this is also at what? 10 volts. Understood? So after TR seconds, if you look at the transmission line, at the source, whatever the voltage you are seeing, the same voltage you are seeing at what? The same voltage you are seeing at load. Understood? Okay, why means here the time period of the signal is very slow. So that means the variation at the input is very slow when compared to what? When compared to is very slow, whereas TR is what? Very fast. The signal is moving very fastly from source to load, but the signal at the source is varying very slowly. Okay, so by the time this signal reaches from source to load, there won't be that much variation at the input. Yes or no? So after TR seconds, if you observe whatever the signal that is present, whatever the value of the signal that is present at source, the same value almost will be present at load. So that means in this case, I can say there is no significant phase shift. There will be no significant phase shift between what? There will be no significant phase shift between source and load. There will be no significant phase shift between what? Between source and load, So that's what we can observe. Yes or no? Okay, whenever T is far greater than what? Whenever T is far greater than TR, we observe that there will be no significant phase shift between what? Between source and load. So whatever the voltage that you are seeing at source, almost the same voltage will be present at load. So that means here at any instant of time, so for next instant of time, so if the next instant of time, what will happen here? This will reach to what? This point will reach to source, and again it is going to vary very slowly. Within TR seconds, it is going to vary very slowly. That means it is going to reach to some other value here. Understood? So the value at the source and the value at the load will be almost what? Will be almost similar. So after a long time, what will happen here? The signal may reach at this location, and at the load also you are going to see the same value at the load. Yes or no? So that means at each and every instant of time, whatever the voltage that is present at the source, almost the same voltage will be present at load. So that means there will be no significant phase shift between what? Between source and load. Yes or no? Okay, so that means here we can happily apply KVL or not? Yes or no? Whatever the voltage that is available at any instant of time, whatever the voltage that is available at the source, the same voltage is available at what? Available at load. So that means KVL is valid here. Understood? So you can happily apply KVL and KCL. You can apply happily KVL and KCL when T is far greater than what? T is far greater than TR. Okay, so there will be no significant phase shift between source and load. So in this case, you can happily apply KVL and KCL. Understood? Okay, so I will explain here. I will explain further. Okay. Just first I am giving brief view. Okay. So then we will see each and everything in detail, right? Next, see here. Now let us consider the time period of the signal here. Now I am applying some high frequency signal here. I am applying high frequency signal at what? At source. So whenever I apply high frequency signal at source, the time period of the signal here, the time period of the signal is what? Is very less. Yes or no? Time period is very less. Time period is very less. Okay, time period is very less, such that now it can be comparable. Now it can be comparable with what? Now it can be comparable with TR, with transit time. Okay, how much small here? High frequency signal at the source. I am applying high frequency signal at the source. So in this case, the time period of the signal is very less, very less, or very small. Understood? Such that now it can be comparable with what here? Now it can be comparable with transit time. Okay, okay. Yeah. So now here, so okay, now it is comparable with what? Now it is comparable with transit time. Now it is comparable with transit time. Okay, now here in this case, T is comparable. T is comparable with what? With transit time. With transit time. So let us assume TR is equal to T by 4. Let us assume TR is equal to T by 4 seconds. So let us assume the transit time is 1/4 of what? 1/4 of the time period of the signal. Let us assume. Okay. So that means here the time period of the signal is comparable with what? Is comparable with the TR, that is transit time. Okay. So now what happens? We will see. So now let us assume the signal I am applying here. I have applied a signal here, right? Okay, so this is at source. And here this is at load. Right? Okay. Now see here. Now let us say at t is equal to 0. So this is the value of the signal at source. Understood? Okay. So after TR seconds here, what happens here? So this this value of the signal will transport from where to where? From source to what? From source to load. So let us say it has moved to this location. Okay. So this is at t equal to 0, and this is at t equal to what? This is at t equal to TR. So after TR seconds, let us say this has moved. After TR seconds, what I have told here? TR is equal to what? TR is equal to T by 4. See, from here to here, this is nothing but what? This is nothing but T. So from here to here, this is nothing but what? This is nothing but T by 4. So that means TR is equal to what? What is the transit time? Transit time is equal to T by 4. So that means from here to here, this is TR seconds. Understood? So at t equal to 0, the signal is present at this location. So after TR seconds, what will happen? This point is going to move to what? Move to load. Understood? So by the time it reaches to the load, what must be the value at source here? The value at source is going to reach at what? It will be at this location. The value of the source will be at this location. Understood? Okay. So after TR seconds, if you observe, the value of the signal is maximum at source, whereas the value of the signal at source will be what? This value is equal to what? This value is at 0. Yes or no? This is 0. Let us say this is 0. Let us say this is 10 volts. Understood? So after TR seconds here, this is the situation you are going to see. Here you are going to have what? 10 volts, and here you are going to have what? You are going to have 0 volts. Understood? Okay. So next what will happen here? Next this 10 volts will transport from source to what? From source to load. So it will transport from source to load. So this is at T is equal to what? T is equal to 2 times of TR. Understood? Okay. After T is equal to 2 times of TR, so this signal is going to travel from where to where? From here to what? From here to there. So by this time, what will happen here? The signal at the source is going to reach to this location, because from here to here it will take what? It will take TR seconds. So at t equal to 2 times of TR, the signal will be at this location here at source, whereas the signal value at the load will be at this location. Understood? So that means there exists what? There exists a significant phase shift here. There exists a significant phase shift between what? Between source and load. Between source and load. Yes or no? Okay. So here in this case, whenever the time period of the signal, comparable to transit time, here we have seen that there exists what? There exists a significant phase shift between what? Between source and load. Understood? Okay. Ramesh, what you are asking here? CCMT. What is that here? Okay, I don't understand what you are asking, Ramesh. Okay. Okay. So here there exists what? There will be a significant phase shift here. There will be a significant phase shift. There will be a significant phase shift between what? Between source and what? Source and load. Between source and load. Right. So there will be a significant phase shift between what? Between source and load. When the time period is comparable what? When the time period is comparable with what? With transit time. So whenever the time period becomes comparable with the transit time, then there exists a significant phase shift between what? Between source and load. Between source and load. Okay. So because of this, what will happen here? So after TR seconds here, if you observe the value of the signal, after TR seconds, this is at TR. Yes or no? This is at T equal to TR. Understood? So after TR seconds, if you observe the value of the signal is at what? Is at 10 volts, and the value of the signal at load is at what? Is at 0 volts. Is at 0 volts. Understood? Okay. So that means at any instant of time, the voltage available at the source is not equivalent to what? Is not equivalent to the voltage available at what? The voltage available at load. So that means here the KVL and KCL are what? KVL and KCL are what? Are ruled out. Yes or no? What do you mean by KVL here? At any instant of time, the voltage that is available at the source must be equivalent to what? The voltage available at the load. Yes or no? But here the voltage available at source is 10 volts, whereas the voltage at the same instant, the voltage available at the load is 0 volts. So that means the voltage available at the source is not same as what? The voltage available at load. Okay. So in this case, the KVL and KCL are ruled out. Okay. Just I have given a brief idea here. What happens whenever T is comparable to TR, and what happens whenever T is very larger than what? Very larger than TR. Understood? Okay. So whenever you apply very low frequency signal such that time period of the signal is becoming far greater than what? Far greater than TR. So in this case there will be no significant phase shift between what? Between source and load. Whenever you apply a high frequency signal such that the time period of the signal becomes comparable with what? Comparable with TR. So in this case there will be a significant phase shift between what? Between source and load. Okay. So in the previous case, KVL and KCL you can happily apply, and in this case KVL and KCL are ruled out. Okay. So we will see these things in detail here. We will see these things in detail. Okay. So we will see these things in detail, right? Counseling for GATE 2021. So I don't have any idea here. Okay. So I will check that and I will let you know, Ramesh. Right? As of now, I don't have any idea. So I will inquire and check that, and if I got any information, I will let you know. Right? Okay. 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 So now, so here I have just told that whenever this is far greater than TR, there will be no significant phase shift between source and load, and whenever T is comparable to TR, there will be a significant phase shift between source and load. Yes or no? So and hence here KVL and KCL are ruled out. In the previous case, KVL and KCL are valid. Yes or no? All these things I have explained. Now we will see these things in some more detail here, right? Okay. So with this you are going to get a crystal clarity here, crystal clarity, right? Okay, so I hope you have understood whatever I have explained previously. So it will become much more clearer, okay, once we cover these things here. Okay, we are going to see the transit time effects in more detail, right? Okay, so see here. So here I am applying the signal. This is source and this is load. This is source and this is load, source and load. So let us say this is x is equal to 0 and let us say this is x is equal to L. So this axis I am considering as x axis, let us assume. Okay, okay. So now see here. That means this length here, this length of the transmission line is L. This length of the transmission line is L, right? Okay. So now let us assume I have applied a signal V0 into cos omega t. I have applied a signal V0 into cos omega t at source. So what will happen here? Whenever I apply a signal at source, what will happen? It is going to shift from source to what? From source to load. Yes or no? It is going to travel from source to what? From source to load. So that means this signal is going to travel from source to load, that is in rightward direction, that means along x direction. So whenever the signal is propagating along x direction, how we can represent here? I have already explained this one here in the previous session, how we have to represent. So this represents V0 into what? Cos of, I can write it as omega t minus what? Omega t minus beta x. Yes or no? Okay, so the signal is shifting from one location to another location. In which direction? In x direction. Yes or no? So I can represent the signal that is propagating along x, I can represent it as what? V0 into cos of omega t minus beta x. Now it has reached to load here. Let us say it has reached to load. So at load it will become what? V0 into what? V0 into cos of omega t minus what? Minus beta L. Minus beta L. Now here x is from here to here, x is varying from where to where here? From 0 to L. From 0 to L. Understood? Okay, so here also I can write cos of omega t minus what? Minus beta x, where x is equal to what? Where x is equal to 0. So that's why we are getting here the signal as what? The signal as V0 into what? V0 into cos omega t. Now it is propagating from where to where? From source to load in rightward direction. So I am representing this as what? V0 into cos of omega t minus beta x. Once it reaches to load, I can represent it as what? V0 into cos of omega t minus beta L. Right? Okay. So now here this beta L here, beta L. So what is this beta L represents here? What is this beta L represents and what is this beta x represents? I have told in the previous session itself here. Beta represents what? Beta is nothing but phase constant. Beta is nothing but phase constant. What it represents here? What it represents? The change in phase per unit length. What is the change in phase per unit length? Yes or no? So beta represents a change in phase per unit length, right? Okay, so that means beta L will represent what here? Beta represents the change in phase per unit length. Beta L represents what? Beta L represents the change in phase over a length L. Yes or no? Beta L represents the change in phase over a length L. The change in phase over a length L. Understood? Okay. Okay. Yeah. So this is what you have to understand here. Beta L represents what? Beta L represents change in phase over a length L. Okay. See, all these things I have explained already in the previous session itself, right? And beta x represents what? Beta x represents the change in phase along what? Change in phase along x. Understood? Okay. 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 So now see here. Okay. So that means here at source we are having V0 into cos omega t, and at load the signal is what? The signal is V naught into what? V naught into cos of omega t minus beta L, and from source to load, the signal is what? V naught into cos of omega t minus what? Omega t minus beta x. So this is the situation, right? Okay. Okay. Now see here. At very low frequencies here, at low frequencies. So I will explain what do you mean by this low frequencies. Okay. So at low frequencies, right? Okay, I will explain here what do you mean by low frequency, right? Okay. See here, at low frequencies, what is this beta L here? Beta L is nothing but what? The change in phase over length L. The change in phase over length L. Understood? So beta L, I can write it as what? I can write it as beta is nothing but what? 2 pi by lambda. Beta is nothing but 2 pi by lambda into what? Into L. So this I can write it as 2 pi into what? 2 pi into L by lambda. 2 pi into L by lambda. Understood? So I said here low frequency here. I said here low frequency. Low frequency means at low frequency lambda value is what? Lambda value is very, very high. Lambda value is very, very high. Yes or no? At low frequencies the lambda value is going to be what? Lambda value is going to be very, very high when compared to what? When compared to L here, when compared to L, that is length of the transmission line. So at low frequencies, what do you mean by low frequencies here? Such that at low frequencies, such that lambda is far greater than what? Lambda is far greater than L. Lambda is far greater than L. Understood? Okay. So at low frequencies such that lambda is far greater than L. So if lambda is far greater than L here, if lambda is far greater than L, so if lambda is far greater than L, so this implies L by lambda will become what? Will become far less than what? Far less than 1. So that means this beta L here, this beta L which is equal to 2 pi into what? 2 pi into L by lambda. So this ratio is very small here. This ratio is very small. So that means it tends to what? It tends to 0. So it may be 0.000001 or it may be 0.00001 or 2, like that. Understood? So it is going to be very small. So L by lambda ratio is very small here. L by lambda ratio is very small. Okay. So or you can consider this ratio is tending to what? Is tending to 0. So in that case here, beta L will become what? If L by lambda ratio is very small and it is tending to 0, then what will happen here? This beta L will also tends to what? This beta L will also tends to what? Tends to 0. So that means beta L here becomes what? Becomes very small. Beta L becomes what? Very small. Understood? So that means here we can neglect, in this case we can neglect what here? We can neglect beta L. So beta L represents what? Beta L represents the change in phase over a length L. Understood? Okay. So we can neglect beta L here. In this case we can neglect beta L. So you can replace beta L with what? Beta L tends to what? Tends to 0. Understood? Okay. So beta L tends to 0 in this case. Right? Okay. So now what will happen? So see here. So beta L, so at low frequencies here, we are dealing with low frequencies. So at low frequencies, this beta L is tending to what? Is tending to 0. Understood? So that means at load, I can write the voltage at load, I can write approximately equal to what? V naught into what? V naught into cos of omega t. Understood? Okay. Now here, if beta L is tending to 0, what happens to beta x? Here x is lying from where to where? X is lying from 0 to what? 0 to L. X is lying from 0 to L. So that means this x value is less than what? Is less than L. So that means this beta x will be very much smaller than what? Than beta L. Yes or no? It is lesser than what? It is lesser than beta L. As beta L is tending to 0 means beta x will also tends to what? Beta x will be further less than what? Further less than beta L. Yes or no? So this beta x will also tends to what? Will also tends to what? Tends to 0. Tends to 0. So that means on the line here, on the line, the voltage will be what? Will be approximately V naught into cos omega t. Understood? And at the source, what you are having? At the source also you are having V naught into cos omega t. So that means at source you are having V naught into cos omega t, and from source to load, that is on the transmission line also you are having the voltage V naught into cos omega t, and at load also you are having V naught into cos omega t. Understood? Okay, so that means if you consider, this is nothing but what? This is nothing but source, and this is nothing but what? This is nothing but load, right? Okay, so if you draw the waveform from source to load, how you are going to get? This is L here, the distance from here to here is L. Okay, so now let us consider at t is equal to 0 here. Let us consider at t is equal to 0. At t is equal to 0. Let us consider at omega t is equal to 0 degrees. So at omega t equal to 0 degrees, what is the voltage at source here? The voltage at source is nothing but what? Is nothing but V naught. And what is the voltage along the line here? At omega t equal to 0, along the line also it is going to be what? It is going to be almost V naught. Yes or no? And at load also it is almost what? It is almost V naught. It is almost V naught. Right? Yes or no? Okay, next at omega t equal to 60 degrees, if I consider at omega t equal to 60 degrees here, 60 degrees. So what is the voltage here? At source, what is the voltage? You are going to have V naught by what? V naught by 2, V naught by 2. And on the line also it is what? It is V naught by 2 only. And at the load, at omega t equal to 60 degrees, at load also the voltage will be what? The voltage will be same, that is V naught by 2. At some other instant of time, you can take at some other instant of time. What you can observe here? What you can observe? Whatever the value that is present at the source, the same value will be present along the line, and the same value of voltage will be present at what? At the load. Understood? So that means what we can conclude here, at any instant of time, the voltage along the line from source to load will be what? Will be same. That means it is independent of what? It is independent of the length of the transmission line. This voltage at any instant of time is not varying along the length. It is not varying along the length. It is constant throughout the length of what? Throughout the length of the transmission line. Yes or no? So that means here we can neglect what? We can neglect the spatial variations of the voltages. Yes or no? Yes or no here? Okay, so at any instant of time, if you observe, the voltage from source to load is almost what? Is almost same. That means this voltage is not varying along what? Along the length. Understood? Okay, so at each and every instant of time, the voltage is constant from source to load. Okay, it is not varying along the length of the transmission line, and hence we can neglect the variations of what? We can neglect the variations of voltage along what? Along the length of the transmission line. Understood? Okay, so here we can simply consider the voltage as a function of what? We can simply consider the voltage as a function of time. See, with respect to time it is varying. Yes or no? But with respect to length it is not varying. Okay, so in this case we can consider the voltage as a function of what? Only time, and whatever the current it is going to generate, that will also become a function of what? That will also become a function of only time. Understood? Now if you observe, whatever the voltage that at any instant of time, whatever the voltage that is present at the source, the same voltage is available at what? The same voltage is available at load. So and hence here you can happily apply what? You can happily apply KVL, and also you can happily apply KCL also. Understood? See, if we are doing the analysis with a voltage signal, the same analysis you can do by taking what? By taking current signal. Understood? Okay, so there is no need to do it twice here. Understood? Okay. So what we can observe here is KVL and KCL are valid, and the voltage and currents are not functions of what? Are not functions of length. Okay, they are functions of only time. We can ignore the variation of these voltages and currents along what? Along length. Okay, so this is what happens at low frequencies here. At low frequencies. Understood? Okay. Next, we'll go for high frequencies here. We'll go for high frequencies. See here, low frequencies means what? Low frequencies means such that lambda must be far greater than what? Far greater than L. Far greater than L. See, or I can represent the same thing in terms of transit time and time period here. In terms of transit time and time period. How? See here. See, L by lambda. This one I can write in this manner. 2 pi into what? 2 pi into, I can write this as L by V into what? Into V by lambda. I am representing the same thing like this here. 2 pi into L by V into what? Into V by lambda. We know that this L by V is nothing but what? Is nothing but transit time, TR. Yes or no? And this is nothing but velocity of the signal. Velocity of the signal, I can represent it as what here? Lambda into what? Lambda into frequency of the signal. Lambda into F. Lambda into F. So here lambda will get cancelled. So you are getting what? 2 pi into what? Into TR into what? F. Lambda will get cancelled. You are having only F here, right? So that is the frequency of the signal. How you can represent the frequency in terms of time period here? That is nothing but 1 by T. So this frequency F, I can represent it as what? I can represent it as 1 by T, right? Okay. So this frequency F, I can represent it as what? I can represent it as 1 by T, 1 by T. So this is equivalent to what? 2 pi into what? 2 pi into TR by T. TR by T. So the same thing here, 2 pi into L by lambda, I can represent in terms of what? TR and what? TR and T. Right? Okay. So here low frequency signal means what? The time period of the signal is very large when compared to what? When compared to transit time. Okay, so you can say the same thing in terms of what? In terms of transit time also. So low frequency such that lambda is far greater than L, or you can say T time period of the signal is far greater than what? Is far greater than TR. Is far greater than TR. Okay. So both mean one and the same here. Both mean one and the same. Understood? At low frequencies such that lambda is far greater than L, or we can say the time period of the signal is far greater than what? Time period of the signal is far greater than TR. So in this situation, this beta L, that is the change in phase over the length L, can be neglected. So once you neglect that, this phase shift beta L is neglected, then at each and every location you are going to have what? You are going to have the same value of the voltage at any instant of time. Understood? Okay. Okay. So I hope it is crystal clear here. I hope it is crystal clear. Right? Okay. So next. Next we will go for case 2 here. Next we will go for case 2, that is at high frequencies. Okay. So what do you mean by high frequencies here? We will see that. Okay, at high frequencies. So what will happen here at high frequencies? So what happens to this change in phase shift along the length L? So beta L is equal to what? Beta L is equal to, I can write it as 2 pi into what? 2 pi by lambda. Beta is 2 pi by lambda into L. So that is equivalent to 2 pi into what? 2 pi into L by lambda. Now see here, this lambda at high frequencies here, the wavelength is going to be what? Is going to be very small. Understood? How much small? So this can be now this wavelength will become comparable to what? Comparable to LR. Now this wavelength will become comparable to what? Comparable to length of the transmission line. Understood? So at high frequencies such that L by lambda ratio is significant. Right? See, at high frequencies means lambda value is what? Lambda value will be very low. So that means this L by lambda ratio will be what? Will be very large, or L by lambda ratio will become what? Will become significant. Understood? So here in this case, since lambda value is very small, L by lambda ratio will become what? Will become significant. Here in this case, the length of the transmission line becomes what? Becomes comparable to what? To wavelength lambda. Okay. So L becomes comparable to what? Comparable to wavelength lambda. Understood? Okay. Okay. See, it is not compulsory that L by lambda ratio must be far greater than 1 like that. Okay. So, if L is equal to lambda by 4, now also you can say it is what? It is comparable with what? L is equal to lambda by 4, then we can say the length of the transmission line is comparable what? Is comparable to wavelength. Is comparable to wavelength. Understood? Okay. Okay. So, it should not be far greater than 1 here. It must be what? It must be comparable to what? It must be comparable to wavelength. It must be comparable to wavelength. So, I will take one problem here, then it is going to be crystal clear. Okay. Okay. So, beta L is equal to, I can write it as 2 pi into L by lambda. So, this L by lambda ratio will become what? Will become significant. Why it becomes significant here? At high frequencies, lambda will be what? Lambda value will be very less, very less. And hence, this L by lambda ratio will become significant. What do you mean by L by lambda ratio significant? Means here L becomes comparable to what? L becomes comparable to wavelength lambda. Okay, so the same thing here, the same thing I can represent beta L, the same thing I can represent beta L in terms of what? In terms of TR by T. How I can represent here? So 2 pi into L by V, I am dividing with V and multiplying with what? V by lambda. Understood? The same thing I am representing in this manner. So L by V I can replace with what? I can replace with TR. I can replace with TR, and this V is nothing but lambda into F. So lambda will get cancelled. So I can write the same thing as what? 2 pi into what? 2 pi into TR divided by what? F I can replace with what? F is nothing but 1 by T. So replace F with 1 by T. So you are going to get what? TR by T. So here you can represent beta L in terms of what? In terms of 2 pi into L by lambda, or you can represent it in terms of what? TR by T ratio. Understood? Now here at high frequencies, the time period of the signal will be what? Very small. The time period of the signal will be very small. So the denominator is very small, means this ratio will become what? This ratio will become significant. This ratio will become significant. See, I am not saying TR by T ratio must be far greater than 1. I am not saying that. What I am saying, that means T is very low, such that TR by T ratio will become what? Will become significant. So that means here T becomes comparable to what? T becomes comparable to what? To TR. Understood? Okay. We know that TR is very small. TR is very small, we know that. Yes or no? So now T also, because at high frequency this time period will also becomes what? Very what I am saying here? We know that TR is very small. Yes or no? Now at high frequencies this time period of the signal will also becomes very small. So such that this time period of the signal and this transit time will become what? Will become comparable at high frequencies. Okay, so at high frequencies, such that L by lambda ratio or TR by T ratio, L by lambda ratio or TR by T ratio becomes what? Becomes significant. So what do you mean by becomes significant here? This ratio, that is L will become comparable to lambda and TR becomes comparable to T. Understood? Okay. Yeah. So now in this case what will happen? We will see. Right? Okay. Yeah. So now in this case, so let us say here you are having source, and here this is nothing but what? This is nothing but load, and at source you are having V0 into cos omega t. And here what is the signal here? Propagating V0 into cos of omega t minus beta x, and here V0 into cos of omega t minus what? Minus beta L. Right? Okay. Yeah. Now see here. Right. Now see here. Now here beta L. So TR by T ratio becomes significant, or L by lambda ratio is becoming significant, means what here? This beta L value will also becomes what? This beta L will also becomes significant. So that means you cannot neglect this beta L value. Understood? Okay. So beta L is nothing but the change in phase over length L. Understood? So you should not neglect this change in phase over length L. So now this becomes what? This becomes significant. Understood? Okay. So you should not neglect here. You should not neglect. It should not neglect beta L. Understood? And hence you should not neglect beta x also. Beta x also should not be neglected. Understood? So now here at source you are having V naught cos omega t, and on the transmission line we are having V naught into cos of omega t minus beta x, and at load we are having V naught into cos of omega t minus beta L. So you should not neglect now beta L. Now here this beta L has become what? Has become significant. This beta L has become significant. You should not neglect. You should not neglect. Understood? Okay. Now see here. Now this is source. So this is source location and this is load location, right? Okay. So this is load and this is source. Okay. Let us assume here. Let us assume I have told that beta L has become significant. Let us assume that significant value beta L is equivalent to pi by 2. Let us assume beta L is equal to pi by 2. Beta L has become pi by 2, or you can say 90 degrees. Pi by 2 or what? Or 90 degrees. Okay. Now it has become significant. Now let us assume beta L value as what? As pi by 2 or 90 degrees. Understood? Now in this case what will happen? See here what will happen. Now at omega t is equal to 0 here, at omega t is equal to 0 degrees, at omega t equal to 0 degrees, what is the value of voltage at source here? So at omega t equal to 0, the source value is at V naught. The source is at V naught. Let us say it is at V naught. Understood? Now whereas load, at load what is the value you are going to have? Tell me. See, beta L is equal to 90 degrees. Beta L is equal to 90 degrees. Now at omega t equal to 0, at omega t equal to 0, what you are going to have? Cos of 0 minus what? 0 minus 90. So cos of minus 90. Cos of minus 90 is how much here? 0. Yes or no? So that means the load will be at what? The load will be at a value 0 volts. 0 volts. Understood? Let us say this is 0 volts here. Right. So the load will be at what? At 0 volts. Understood? So that means at the source the value of the voltage will be at V naught, and at load the value of the voltage is at what? Is at 0. So this is along the length. This is along the length of what? Along the length of transmission line. So what will happen? Here it is at V naught. Here it is at 0. So the signal will be like this. This is at what? This is at omega t equal to what? Omega t equal to 0. This is at omega t equal to 0. Right? Okay. So this is the situation. This is the signal. This is the voltage signal that is present on the transmission line. So at source it is having maximum value, and at load it is having what? 0 value. So it is varying from source to load in this manner at omega t equal to 0. Right? Okay. Next, if you consider at omega t equal to 90 degrees here, if you consider at omega t equal to 90 degrees, at omega t equal to 90 degrees. Understood? Okay. So at omega t equal to 90 degrees. So at omega t equal to 90 degrees, what is the value of the voltage at source here? The value of the voltage at source will be what? At source will be 0. Right? Okay. Next, what is the value of the load? What is the value of the voltage at load here when omega t equal to 90 degrees? So 90 minus beta L is what? Beta L is 90. So 90 minus 90 will become what? Will become 0. So that means cos 0. Cos 0 is 1. So that means the voltage at load will be what? Will be at V naught. V naught. Understood? So the voltage at source will be what? Will be at 0, and the voltage at load will be at what? Will be at V naught. So that means the voltage along the transmission line is varying like this. It is varying like this. So this is at what? This is so this is at omega t is equal to what? Omega t is equal to 90 degrees. Understood? So this is at one instant of time, that is at omega t equal to 0, and this is at another instant of time. So at that instant of time, what is omega t value is equal to 90 degrees. So at this instant of time, this is how the voltage is varying from source to what? From source to load. And at another instant of time, this is how the voltage is varying from source to load. Yes or no? Okay, so that means here, now what happens here, the voltage as you move along the length of the transmission line, the voltage is varying, the voltage is varying, the voltage is varying along the length of what? Along the length of transmission line. Understood? Okay, and the values of the voltages are also varying with respect to what? With respect to time. See, this is at instant omega t equal to 0, and this is at instant omega t equal to 90, right? So at omega t equal to 0, the value at the source will be V0, and at omega t equal to 90, the value of at the source will be 0 volts. So that means now the voltage is also varying with respect to what? With respect to time, and also it is varying with respect to what? With respect to length. So that means here the voltage will become function of what? Function of both space as well as what? As well as time, as well as time. So, and hence if you do the same analysis with respect to current, we can prove that the current will also becomes a function of what? Current will also become a function of space and time, space and time. Okay. So, and I will also become a function of what? Space and time. So now in this case, that means whenever we are dealing with high frequencies here, whenever we are dealing with high frequencies, such that, what do you mean by high frequencies? Such that L by lambda ratio or TR by T ratio must become what? Must become significant. So under this condition, what will happen? The voltages and currents on the transmission line will become what? Will become functions of both space as well as what? As well as time, as well as time. So now here you cannot ignore the spatial variations. Why? Here because they have become what? They have become significant here. Yes or no? You should not neglect that. Okay, okay. So that's what happens at high frequencies. Now see here, at omega t equal to 0, the voltage at source is V0, and the voltage at load is what? At load is 0. Understood? So, and the voltage is varying at this instant of time. After TR seconds, if you observe, you are going to see the voltage variation like this here. Yes or no? You are going to see the voltage variation like this. Understood? So that means whatever the voltage that is present at source is not same as what? Is not same as the voltage present at load. Understood? Okay. It is varying throughout what? Throughout the length of what? Throughout the length of the transmission line. And hence here you cannot apply what? You cannot apply KVL and KCL. Here you cannot apply KVL and KCL. So here in this case, KVL and KCL are what? Are ruled out. Are ruled out. You cannot apply. So once the voltages and currents, becomes functions of both space and time, then in that case you cannot apply what? You cannot apply KVL and KCL. They are ruled out. Yes or no? Okay. 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 So here at any instant of time, the voltage at source is not same as what? Is not same as the voltage at load. Understood? And hence KVL is not valid. KVL is not valid, and we can prove in the same manner KCL is also not valid. Okay. Okay. Yeah. So okay. Yeah. So these are the effects of what? These are the effects of transit time here. These are the effects of transit time. See, whenever the time period of the signal is far greater than TR, then we can neglect what? We can neglect the transit time and all those things. We can neglect the transit time and all those things, and we can ignore the transit time effects. We can ignore the transit time effects. So in that case, the voltages and currents will become what? Will become only a functions of time. And here the KVL and KCL are valid. Right, and once we go to high frequencies such that TR by T ratio will become what? Will become significant. That means TR will become comparable to what? Comparable to time period of the signal. Now in this case, you should not ignore what? You should not ignore this TR. You should not ignore this TR. That means you should not ignore here transit time effects. You should not ignore here transit time effects. That means you have to include what is the time taken by the signal to travel from source to load. You cannot neglect that. Okay, because now here this TR becomes comparable to what? Comparable to this time period of the signal. In that case, you have to, you should not neglect, in this case, you should not neglect the transit time, and hence here the transit time effects will come into picture. So because of this, what happens here? Because of this transit time effects, what happens? Voltages and currents will become functions of what? Functions of both space as well as what? As well as time. Understood? Okay. So once they become functions of space and time, then you have to, you should not apply what? You should not apply KVL and KCL, right? Okay. 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 So I think it is crystal clear here, right? Okay. Okay. So I will give one simple problem here. I will give you one simple problem. You have to do it as homework here, just for practice, right? Okay. So let us consider a transmission line. Let us consider a transmission line, okay, and let us consider its length L is equal to 30 by 4 centimeters. Let us assume its length is L is equal to 30 by 4 centimeters, right? And the velocity of the signal is equal to 3 into 10 to the power of 8 meters per second. Let us assume the velocity of the signal is 3 into 10 power 8 meters per second, right? Okay, and here this is source, right? This is source. Okay, so at source, let us assume you are applying a signal. In the first case, let us assume you are applying a signal whose frequency f is equal to 1 kilohertz, and in the second case, you are applying the signal whose frequency, let us say this is f1, and now you are applying a frequency f2. Its value is equal to what? 1 gigahertz. Its value is equal to 1 gigahertz. Understood? Okay, so you just check so this is f1 is equal to 1 kilohertz, and here I have given f2 is equal to what? 1 gigahertz. You just check when you can neglect transit time effects and when we have to include transit time effects. That means when the transit time effects will become significant and when the transit time effects will become what? Can be ignored. Okay, so that's what you have to check from these two here, So in the first case, what I have done here, we have applied a signal whose frequency is equal to what? Whose frequency is 1 kilohertz. So that means we know that it is a low frequency signal. Okay, see, when we can neglect the transit time effects here, you should not say simply low frequency. You should say low frequency such that at that frequency, what must be the condition? L by lambda ratio or TR by T ratio can be what? Can be ignored, right? Yes or no? Okay. So here you have to check whether lambda is far greater than L or time period is far greater than TR. You have to check this one. Understood? Okay, you have to check these things for both the cases here, Understood? So if this ratio becomes if lambda is far greater than L or T is far greater than TR, then we can ignore what? We can ignore the transit time effects. Understood? Okay, so just do it as a practice here, just check these things here, check these things for first question and second question, right? Okay, right? Okay, so this is all about transit time effects here. Okay, so that's why you will be said that circuit theory or network theory is not valid at very high frequencies. It is valid at only low frequencies, Yes or no? So what do you mean by low frequency? Such that L by lambda ratio or TR by T ratio will become what? Will become negligible, or beta L will become what? Will become negligible. Understood? So in that case, we can ignore the transit time effects and you can happily apply KCL and KVL. So in this region, the network theory is valid. Understood? So once you enter into high frequencies means such that TR by T ratio or L by lambda ratio will become what? Will become significant. In this case, the change in phase shift over the length L, that is beta L, will become significant. So in this case, the voltages and currents will become what? Will become functions of both space as well as what? As well as time. So here the transit time effects will come into play. Understood? You should not ignore them. Right. So once the voltages and currents becomes a functions of both space and time, you cannot apply what? You cannot apply KVL and KCL, and hence your network theory will be ruled out at high frequencies. Understood? So always remember, high frequencies means such that L by lambda ratio becomes significant, or TR by T ratio becomes significant, or beta L becomes significant. So these things you have to understand. Okay. Okay. You should not say simply high frequency and low frequency. What do you mean by high frequency? Okay, what do you mean by low frequency? That also you have to specify. Low frequency means L by lambda ratio or TR by T ratio or beta L can be what? Can be ignored. Okay, high frequency means such that L by lambda ratio or TR by T ratio or beta L will become what? Will become significant. Okay, okay. So with this I am winding up the session for today, and tomorrow exactly at 10 a.m. here. Tomorrow exactly at 10 a.m. we are going to start the session. Right. So daily in our Gate Academy Global channel, daily there will be an EMT session at 10 a.m. here. Now we are dealing with the topic transmission lines. Right. Okay. So it is exclusively for what? It is exclusively for EC students. Right. Okay. Okay. So with this I am winding up the session, and we will meet tomorrow exactly at the same time, that is 10 a.m. So until then, take care. Bye bye.